In the last talk, we have discussed so much about the crystallinity and the amorphous nature of a polymer. The interesting thing is that with respect to temperature, the polymer can actually change its physical property in a very drastic manner, not unlike many of the other solids, and that important temperature is also known as the glass transition temperature of a polymer. So we are going to talk about this glass transition temperature because that is what is very important in terms of the nature of the polymers. So we are talking about what is the glass transition temperature, the experimental methods to determine Tg, and the factors that affect the glass transition temperature. Now, what is this glass transition temperature, which actually changes the nature of the polymer very drastically? Well, it is actually the temperature that a polymer, the transition happens in a polymer when it goes from rubbery to the rigid states. Now, you need to little bit of imagine this. I told you that the polymer has a very long chain. Now, this long chain, if there is enough energy in the long chain, then there will be enough movement between the interlinks. But if there is not enough energy there, so suppose I consider the polymer like this, that you have a long chain system. Okay. Now, if you have enough energy, what will happen is that each one of these links will move against the other. So you can get some kind of a motion. That means it can actually kind of adjust itself. Now, if that happens, then the polymer will be in its rubbery stage. That means the temperature is such that it can actually move the links against each other. On the other hand, if it is at a very low temperature level, that very low is of course relative. For example, for polyethylene, it is like minus 110, whereas for polyester PET it is only about 69 degree. But at a particular such critical temperature, it will happen that these chains will lose its mobility. It will become rigid, it will not be able to move against each other. At that stage, that is below the Tg, it will behave almost like a glassy material. That means it will behave like it is hard and brittle. You can actually do this test very well if you have a refrigerator in your room. What you need to do is that you take for example, a polyethylene packet. Now, polyethylene, let us look at it, that is minus 90, so that is quite low for you to achieve in the regular system. But something like, let's say, of course, if you cool nylon, you take a nylon rope and you cool it. What you will find is that, in fact, that is what you will find in the winter time with nylon, is that it will become very hard and brittle. You can break it very easily. So that means it has reached that glassy stage where the chains are not able to move against each other. So that's why is the glass transition temperature is so important for us, because this happens uniquely to polymers and it actually happens in the amorphous state. Now, how we are getting this, let us try to look at it, that suppose you have a polymer melt in a liquid stage. As I am cooling in the supercooled liquid form, that means cooling at a faster rate, I am going to directly come into the glassy stage. If you cool it very slowly, then there is a chance of crystallization and then you may get a crystalline solid. So the difference between a crystalline solid and glassy solid is that you are actually supercooling the particular solid from the liquid stage. Now hard plastics like polystyrene and PMMA, they are generally used below their glass transition temperature. That means they are generally used at the glassy state itself, because their TGs are well above room temperature, around 100 degrees centigrade. On the other hand, those which we normally use as elastomers like rubbers, polyisobutylene, polyisobutylene, etc., they are used above their TGs in the rubbery stage. That is why they are quite soft and flexible. That means if you really cool them, you will get them in their glassy stage. So here is like a liquid, you are quickly cooling, supercooled, you are getting a glassy stage. You are cooling little bit slowly, you are going to get to semi-crystalline solid. And if you are cooling it really very slowly, then you are going to go to the crystalline solid stage. So the curve A is for the amorphous polymer, curve B is those polymers which are semi-crystalline, curve C are those which are like hypothetical, but those which are very crystalline. Now let us look into the behavior of in general any viscoelastic polymer, which is not like a thermoset polymer, where actually, because for thermoset polymer, because of that chemical cross-linking, because of the chemical cross-linking in thermoset polymers, you will not be able to achieve the rubbery stage in a thermoset polymer. But if you consider a thermoplastic polymer, you will find that it is having 5 regions in it. Phase 1, which is the glassy region, you will get it here, and then phase 2, which is like leathery glassy transition region. Then you get phase 3, which is like a rubbery region. Then you get phase 4, which is like a rubbery flow region, and phase 5, which is like a viscous flow liquid. So phase 1, which is glassy region, the telltale signs are that it has relatively high modulus, very hard, high resistance to flow, as I told you, because chains are not mobilized enough. Second phase, your transition is happening, so there is a sharp decrease in the elastic modulus. As you can see, it is falling down, deformation not totally recoverable. Then the rubbery region, where it is both elastic and viscous components are present. Modulus falling rate has stabilized, elastic high strain rate, and viscous has a low strain rate. Then you have the rubbery flow region, where the viscosity starts to dominate, modulus starts to fall again, and you have the viscous flow region, where the modulus drops very steeply. Of course, the final phase is the decomposition. Now, what is the effect of temperature in a viscoelastic material? We consider 2 types. One is totally amorphous. Here you will see that all the regions are present. That means from the glassy till leathery, rubbery, viscous, you get all the regions. Whereas if it is 100% crystalline, then you get the glassy phase, and then you will not get the rubbery transition phase, but it will just come down sharply to the flow region. So you get one single melting point and it comes down. So as the crystallinity decreases, this nature is becoming more and more, this S type of nature will be becoming more and more predominant for a solid, for a viscoelastic material. Similarly, from the cross-linking point of view, if there is no cross-linking, that means it is like a thermoplastic material, thermoplastics, you are going to see all these regions very predominantly. But as the cross-linking increases, like thermosets here, in this case thermoset material, here you are not going to see these changes anymore. Why? Because I told you, since the polymer is already linked, heavily networked, So even if you change the temperature, you are not going to gain in terms of the mobility of the links. So basically, for the thermoset materials, you may not even get a melting point, it will straightforward degrade into the gaseous phase in many cases. Now, how do we measure the glass transition temperature? There are several methods. One of the very popular one is known as DSC, differential scanning calorimetry. And here you need to take two different materials. One material, the sample, which has a glass transition temperature at that particular temperature where you think this is happening, and the other case is the reference material which do not have the glass transition at that particular temperature. Now, because you can control the heating in the pan, so you can actually find out that what is the heat flow, that means heat per unit time. By the help of temperature sensors, you can also measure both for the sample as well as for the reference what is the temperature increase with respect to time, that means the heating rate. The ratio of the two is going to give you the heat capacity, and the glass transition, if it happens, the heat capacity changes significantly. In fact, if you look at the curve, you would see that if there is a glass transition, then the heat flow is affected and it is significantly changing. So, from this you can actually say yes, there is a glass transition happening by comparing this with the reference material which would not show this type of a change or this type of a shape. So, we have to keep in mind that this change does not occur suddenly but takes place over a temperature range. In fact, that is why we have to take these two tangents and then find out, and we usually just take the middle of the incline to be the Tg, and the graph shows that the polymers have a higher heat capacity above the glass transition temperature. So, usually higher the Tg, higher is the cross-linking density, and vice versa. We can say that higher cross-linking density, higher will be the glass transition temperature. So, DSC is one way to measure. What are the other ways? The other very popular way is called thermomechanical analysis or TMA. Now, unlike the heat capacity, what we measure here is actually the coefficient of thermal expansion, because that also with respect to the glass transition, you would see that the coefficient of thermal expansion, either you test it in a longitudinal expansion or in flexure, in both the cases you would see that the coefficient of thermal expansion changes a lot, and by drawing similarly two tangents, the intersecting point, you will be able to find what is the glass transition temperature in this particular case. So, thermomechanical analysis techniques such as expansion, flexure or penetration, they can be used for Tg, and in expansion TMA is the coefficient of thermal expansion which is directly measured as a function of temperature, and the Tg in a polymer corresponds to the point in the expansion curve where the free volume begins to allow for the greater chain mobility. As the temperature rises past the Tg, the adhesive will begin to soften or lose some tensile strength and also experience a rise in the CT, the coefficient of thermal expansion. The third method, which is also a very interesting method, is known as dynamic mechanical analysis or DMA. What we do here is that, much unlike the change of temperature, here we generally change the temperature in a very small scale, but we actually subject this polymer to stress, and it is a sinusoidal stress that we apply, and we try to find out that what is the strain. So, here is the the stress, for example, you are plotting, and you are also measuring the strain and you are plotting it. You see there is a phase difference between the two. Now, this phase difference, if you look at the amplitude here and if you look at the amplitude here of the strain, then there is a phase difference delta. This phase difference delta is a measure of the loss or viscoelasticity in the material. And the frequency at which this happens is known as the critical frequency, and the temperature when this happens is known. If you actually plot this loss factor with respect to temperature, you would see that tan delta, if you plot with respect to temperature or frequency, you will see there is a glass transition temperature Tg where this loss will be maximum. Now at this juncture I need to tell you that much unlike the metallic or the ceramic counterparts, the modulus of elasticity for a polymer is actually always complex. It has two parts. One is the storage modulus E prime and another is the loss modulus, which is E double prime. So if you find out the stress in a cycle, sigma 0 sin omega t plus delta strain is sin omega t, then there is a difference. You can do it the other way also. That means you can put sigma t as sigma 0 sin omega t, and you can observe the change in epsilon depending on whatever you like. It will become sin omega t plus delta. So the phase difference either from the strain or from the stress. Now for a purely elastic case, this delta is actually 0. So that means stress and strain, they are exactly at the same phase. For a purely viscous case, this delta is actually pi by 2, which means the stress and strain are actually in a 90-degree opposite phase. And for viscoelastic material, it is always in between the two. Now this tan delta, which is also a measure of the loss, the energy that is dissipated in the system, can be actually expressed as a ratio of the E double prime to E prime, that is the loss modulus to the storage modulus of the sample. So if tan delta is high, that means the material is highly viscoelastic. It can actually, enormous amount of energy it can dissipate, and particularly that happens at the glass transition temperature when the chains have just reached enough mobility. So the delta value ranges between 0 to 90 degree, and as delta approaches 0 degree, you get purely elastic behavior. As delta approaches 90 degree, purely viscous behavior, and delta in between the two is actually viscoelastic material. At the glass transition temperature, the storage modulus decreases dramatically, I told you, and the loss modulus reaches a maximum. So this is the real modulus or the storage modulus. So as the glass transition, the storage modulus is decreasing. On the other hand, at the glass transition, so E prime is decreasing. On the other hand, just like the tan delta, at the glass transition you will find that if you plot it E double prime, you will find it is going to behave almost the same manner as the tan delta. That means at the glass transition temperature, the E double prime, so this is the E double prime, that is actually showing the peak. So that is kind of comparison between the two. What are the factors that affect this glass transition temperature? Well, one is the chain length. The higher the chain length, the more will be this. Chain stiffness, plasticizers, cross-linking and copolymers. Let's look at them one by one. If you look at the chain length, as molecular weight increases, the Tg increases. We know that. So high density of branches will actually reduce the chain mobility. Cross-linking will actually restrict the molecular motion. And as the molecular weight decreases, Tg also decreases, because there is easier movement of molecules and more inherent free volume in the polymer. So in any polymer, there is something called Tg infinity, that is the glass transition temperature at infinite chain length. There is a polymeric constant and molecular weight of the particular polymer. So you can, if you know Tg infinity C and the molecular weight, you can actually find out what is Tg. For example, for PVC, Tg infinity is 351, C is this. Like that for PMMA or polystyrene. Now for the chain stiffness, this is controlled by the ease of rotation about the chemical bonds. So if you have presence of double bonds or aromatic groups, this will definitely lower the chain flexibility and thus it will increase the Tg. If you have bulky large side groups, that will restrict the chain rotational freedom and flexibility, so you are going to get an increase in terms of Tg. For example, you consider polypropylene. You check the presence of double bond and aromatic rings. So if you consider polypropylene with polyester, you will see that polyester has actually higher Tg or higher melting point temperature, mostly because it has actually more number of double bonds and the aromatic rings. You can see the aromatic rings and double bonds. Similarly, if you consider the methyl side group, which is heavier than hydrogen atom between polyethylene and polypropylene, you can see here that the polypropylene has this particular heavy side group, so its Tg is actually higher in comparison to the Tg of polyethylene. So thus the chain stiffness definitely changes the Tg. Many times we use plasticizers, that means some kind of additives which increases the chain movement, like phthalate esters in PVC improves the flexibility and durability. So addition of plasticizer can actually reduce the Tg significantly. And in terms of cross-linking, if you can reduce the chain mobility, then the Tg will be increased. So thus you can add chemicals to do this process. If you add copolymers, now every copolymer, or so to say every polymer, has its own glass transition temperature. So if you have two polymers, then you have two glass transition temperature, and if there are two different weight fractions, by using this formula you can actually find out what is the Tg, and naturally the Tg will be different from Tg1 and Tg2. So thus copolymer can affect the glass transition temperature. So this is where we will put an end about the effects of these things, of various things like the chain length, the chain stiffness, okay, the presence of the the side grooves, for example, okay, and also another point I didn't tell you, that the pressure and tacticity, they can also affect the glass transition temperature. In the next lecture, we will learn about the polymer mechanical properties and the factors that affect these properties. Thank you.